Hi, I'm back again reading the third edition of Python Programming: An Introduction to Computer Science, written by John Zelle. Uh, we are we are in chapter 2 today, writing simple programs, and we'll get right into it, starting with objectives. In this chapter, the objectives are 1, to know the steps in an orderly software development process. 2, to understand programs following the input process output IPO pattern and be able to modify them in simple ways. Third, to understand the rules for forming valid Python identifiers and expressions. And finally, to be able to understand and write Python statements to output information to the screen, assign values to variables, get information entered from the keyboard, and perform a counted loop. So 2.1, the software development process. As you saw in the previous chapter, it is easy to run programs that have already been written. The harder part is actually coming up with a program in the first place. Computers are very literal, and they must be told what to do, right down to the last detail. Writing large programs is a daunting challenge. It would be almost impossible without a systematic approach. A process The process of creating a program is often broken down into stages according to the information that is produced in each phase. In a nutshell, here's what you should do. Number 1, analyze the problem. Figure out exactly what the problem to be solved is. Try to understand as much as possible about it. Until you really know what the problem is, you cannot begin to solve it. Number 2, determine specifications. Describe exactly what your program will do. At this point, you should not worry about how your program will work, but rather about deciding exactly what it will accomplish. For simple programs, this involves carefully describing what the inputs and outputs of the program will be and how they relate to one another. 3, create a design. Formulate the overall structure of the program. This is where the how of the program gets worked out. The main task is to design the algorithm or algorithms that will meet the specifications. Number 4, implement the design. Translate the design into a computer language and put it into the computer. In this book, we will be implementing our algorithms as Python programs. And 5th, test or debug the program. Try out your program and see whether it works as expected. If there are any errors, often called bugs, then you should go back and fix them. The process of locating and fixing errors is called debugging a program. During the debugging phase, your goal is to find errors. So you should try everything you can think of that might, quote unquote, break the program. It's good to keep in mind the old maxim: nothing is foolproof because fools are too ingenious. Number 6, maintain the program. Continue developing the program in response to the needs of your users. Most programs are never really finished. They keep evolving over years of use. Now we go on to 2.2, an example program, the temperature converter. Let's go through the steps of the software development process with a simple real-world example involving a fictional computer science student, Susan Computewell. Susan is spending a year studying in Germany. She has no problems with language, as she is fluent in many languages, including Python. Her problem is that she has a hard time figuring out the temperature in the morning so that she knows how to dress for the day. Susan listens to the weather report each morning, but the temperatures are given in degrees Celsius, and she is used to Fahrenheit. Fortunately, Susan has an idea to help solve the problem. Being a computer science major, she never goes anywhere without her laptop computer. She thinks it might be possible that a computer program could help her out. Susan begins with an analysis of her problem. In this case, the problem is pretty clear. The radio announcer gives temperatures in degrees Celsius, but Susan only comprehends temperatures that are in degrees Fahrenheit. Next, Susan considers the specifications of a program that might help her out. What should the input be? She decides that her program will allow her to type in the temperature in degrees Celsius. And the output, the program will display the temperature converted into degrees Fahrenheit. Now, she needs to specify the exact relationship of the output to the input. Susan does some quick figuring. She knows that 0 degrees Celsius, or freezing, is equal to 32 degrees Fahrenheit, and 100 degrees Celsius, or boiling, is equal to 212 degrees Fahrenheit. With this information, she computes the ratio of Fahrenheit to Celsius degrees as 212 minus 32 0 is equal to 180 over 100, which is equal to 9 over 5. Using F to represent the Fahrenheit temperature and C for Celsius, the conversion formula will have the form F equals 9/5 C plus K for some constant K. Plugging in 0 and 32 for C and F, respectively, Susan immediately sees that K is equal to 32. So, the final formula for the relationship is F equals 9/5 C plus 32. That seems an adequate specification. Notice that this describes one of many possible programs that could solve this problem. If Susan had a background in the field of artificial intelligence, she might consider writing a program that would actually listen to the radio announcer to get the current temperature using speech recognition algorithms. For output, she might have the computer control a robot that goes to her closet and picks an appropriate outfit based on the converted temperature. This would be a much more ambitious project, to say the least. Certainly, the robot program would also solve the problem identified in the problem analysis. The purpose of specification is to decide exactly what this particular program will do to solve the problem. Susan knows better than to just dive in and start writing a program without first having a clear idea of what she's trying to build. Susan is now ready to design an algorithm for her problem. She immediately realizes that this is a simple algorithm that follows a standard pattern: input, process, output, or IPO. Her program will prompt the user for some input information, the Celsius temperature, process it to produce a Fahrenheit temperature, and then output the results by displaying it on the computer screen. Susan could write her algorithm down in a computer language. However, the precision required to write it out formally tends to stifle the creative process of developing the algorithm. Instead, she writes her algorithm using pseudocode. Pseudocode is just precise English that describes what a program does. It is meant to communicate algorithms without all the extra mental overhead of getting the details right in any particular programming language. Here is Susan's completed algorithm. Input the temperature in degrees Celsius. Call it Celsius. Calculate Fahrenheit as 9/5 Celsius plus 32. Output Fahrenheit. The next step is to translate this design into a Python program. This is straightforward, as each line of the algorithm turns into a corresponding line of Python code. $convert.py. $, a program to convert Celsius temps to Fahrenheit. $, by : Susan compute well. Def main. open parentheses, close parentheses, colon. Celsius equals eval, open parentheses, input, open parentheses, open quote. What is the Celsius temperature, question mark, close quote, close parentheses, close parentheses. Fahrenheit equals 9/5 or 9/5. Use the asterisk, Celsius plus 32. Print, open parentheses, open quote. The temperature is, close quote, comma, Fahrenheit, comma, open parentheses, degrees Fahrenheit, period, close quote, end parentheses. Main, open parentheses, close parentheses. See if you can figure out what each line of this program does. Don't worry if some parts are a bit confusing. They will be discussed in detail in the next section. After completing her program, Susan tests it to see how well it works. She uses inputs for which she knows the correct answers. Here is the output from two of her tests. What is the Celsius temperature? 0. The temperature is 32.0 degrees Fahrenheit. What is the Celsius temperature? 100. The temperature is 212.0 degrees Fahrenheit. You can see that Susan used the values of 0 and 100 to test her program. It looks pretty good, and she is satisfied with her solution. She is especially pleased that no debugging seems necessary, which is very unusual. Section 2.3, Elements of Programs. Now that you know something about the programming process, you are almost ready to start writing programs on your own. Before doing that, though, you need a more complete grounding in the fundamentals of Python. The next few sections will discuss technical details that are essential to writing correct programs. This material can seem a bit tedious, but you will have to master those basics before plunging into more interesting waters. Section 2.3.1, Names. You have already seen that names are an important part of programming. We give names to modules, for example, convert, and to the functions within modules, for example, main. Variables are used to give names to values, for example, Celsius and Fahrenheit. Technically, all these names are called identifiers. Python has some rules about how identifiers are formed. Each identifier must begin with a letter or underscore, the quote character, which may be followed by any sequence of letters, digits, or underscores. This implies that a single identifier cannot contain any spaces. According to the rules, all of the following are legal names in Python: X, Celsius, spam, spam2, spam and eggs, spam underscore and underscore eggs. Identifiers are case sensitive, so spam, capital S spam, capital P in the middle of spam, and all caps spam are all different names to Python. For the most part, programmers are free to choose any name that conforms to these rules. Good programmers always try to choose names that describe the thing being named. One important thing to be aware of is that some identifiers are part of Python itself. These names are called reserved words or keywords and cannot be used as ordinary identifiers. The complete list of Python keywords is shown in Table 2.1. It's here. Pardon the highlighter. This is a used book, but this page over here, let me hold it up to the camera. It's not working well. Oh, camera. You're going to stand up and point this to the camera. There we go. That is the complete list. 2.1. And these are words that are already part of the Python program. And I will read them for you. Down the first column, false, none, true, and, as, assert, break. And then the second column, class, continue, def, del, elif, else, except. And the next column, finally, for, from, global, if, import, in. And the next, in, lambda, non-local, not, or, pass, raise. And the final column, return, try, while, with, yield. So these are the Python keywords according to Table 2.1. Python also includes quite a number of built-in functions, such as the print function that we've already been using. While it's technically legal to use or reuse the built-in function name identifiers for other purposes, it is generally a very bad idea to do so. For example, if you redefine the meaning of print, then you will no longer be able to print things out. You will also seriously confuse any Python programmers who read your program. They expect print to refer to the built-in function. A complete list of the built-in functions can be found in Appendix A. So even this Table 2.1 isn't a complete list. Now, Section 2.3.2, Expressions. Programs manipulate data. So far, we have seen two different kinds of data in our example programs, numbers and text. We'll examine these different data types in great detail in later chapters. For now, we just need to keep in mind that all data has to be stored on the computer in some digital format, and different types of data are stored in different ways. The fragments of program code that produce or calculate new data values are called expressions. The simplest kind of expression is a literal. A literal is used to indicate a specific value. In chaos.py, you can find the numbers 3.9 and 1. The convert.py program contains 9, 5, and 32. These are all examples of numeric literals, and their meaning is obvious. 32 represents, well, 32, the number 32. Our programs also manipulated textual data in some simple ways. Computer scientists refer to textual data as strings. You can think of a string as just a sequence of printable characters. A string literal is indicated in Python by enclosing the characters in quotation marks. If you go back and look at our example programs, you will find a number of string literals, such as, in quotes, hello, and enter a number between 0 and 1, end quote. These literals produce strings containing the quoted characters. Note that the quotes themselves are not part of the string. They are just the mechanism to tell Python to create a string. The process of turning an expression into an underlying data type is called evaluation. When you type an expression into a Python shell, the shell evaluates the expression and prints out a textual representation of the result. Consider this small interaction. Arrow, 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 32. Next line, 32. Arrow, 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 in quotes, hello. The following line, single quotes, hello. Arrow, 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 open quote, 32, close quote. Next line, single quote, 32, single quote. Notice that when the shell shows the value of a string, it puts the sequence of characters in single quotes. This is a way of letting us know that the value is actually text, not a number or other data type. In the last interaction, we see that the expression 32 produces a string, not a number. In this case, Python is actually storing the characters 3 and 2, not a representation of the number 32. If that's confusing right now, don't worry too much about it. It will become clearer when we discuss these data types in later chapters. A simple identifier can also be an expression. We use identifiers as variables to give names to values. When an identifier appears as an expression, its value is retrieved to provide a result for the expression. Here is an interaction with the Python interpreter that illustrates the use of variables as expressions. Arrow, 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 x minus 5. Arrow, 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 x. No, that's not a minus, that's an equals. Sorry, back to the beginning of the expression. Arrow, 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 x equals 5. Arrow, 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 x. Next line, 5. Arrow, 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 print, open parentheses, x, close parentheses. Next line, 5. Arrow, 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 sprint, no, not sprint, print, in parentheses, spam. Trace back most recent, in parentheses, most recent call last, close parentheses, colon. Next line, file, quote, left facing arrow, STDIN, right facing arrow, end quote, comma, line 1, comma, in, left facing arrow, module, right facing arrow. Next line, name error, colon, name, single quote, spam, end single quote, is not defined. One is assigned to the value 5. Asking Python to evaluate the expression type, so it has recognized it, which is the value that we had just assigned to x. Of course, we get the same result when we explicitly ask Python to print x using a print statement. The last interaction shows what happens when we try to use a variable that has not been assigned a value. Python cannot find a value, so it reports a name error. This says that there is no value with that name. The important lesson here is that a variable must always be assigned a value before it can be used as an expression. More complex and interesting expressions can be constructed by combining simpler expressions with operators. For numbers, Python provides the normal set of mathematical operations: addition, subtraction, multiplication, division, and exponentiation. The corresponding Python operators are plus, minus, asterisks, forward slash, and asterisk, asterisk. Here are some examples of complex expressions from chaos.py and convert.py. 3.9 asterisk x asterisk open parentheses 1 minus x close parentheses, next line, 9/5 asterisk Celsius plus 32. Spaces are irrelevant within an expression. The last expression could have been written 9/5 asterisk Celsius plus 32, and the result would have been exactly the same. That example has no spaces in it. Usually it's a good idea to place some spaces in expressions to make them easier to read. Python's mathematical operators obey the same rules of precedence and associativity that you learned in your math classes, including using parentheses to modify the order of evaluation. You should have little trouble constructing complex expressions in your own programs. Do keep in mind that only the round parentheses are allowed in numeric expressions, but you can nest them if necessary to create expressions like this. Here we go again. Open parentheses, x1 minus x2, end parentheses. /2 asterisk n close parentheses plus open parentheses spam /k asterisk 3 end parentheses. By the way, Python also provides operators for strings. For example, you can quote unquote add strings. Arrow, quote bat plus quote man. Next line says Batman in single quotes. This is called concatenation. I'm going to go with that. I've never heard this word before. I'm making it up. Concatenation. As you can see, the effect is to create a new string that is the result of gluing the strings together. You'll see a lot more string operations in Chapter 5. Good. Maybe I'll understand this new word then.